In this brief video we're going to look at the units that we are going to be using in our work in mechanics. Over the past couple of hundred years, a great deal of time and effort has been spent developing clear and rigorous definitions of the units to be used in science. Within mechanics we're going to use three basic SI units. For the measurement of length, the basic unit is the meter. For the measurement of mass, the basic unit is the kilogram. And for the measurement of time, the basic unit is the second. Now, using these three base units as building blocks, we obtain derived SI units for a wide range of quantities. So, for example, area is length times breadth. So the unit, the SI unit for area, is going to be the unit of length times by the unit of breadth. In other words, meters times by meters. In other words, meters squared. And 1 meter squared is the area of a square of side 1 meter. Similarly, volume can be regarded as being area times height. We know that the unit of area is meters squared. We know that the unit of height is the meter. So therefore the unit of volume is meters squared times by meters. In other words, meters cubed. And we've got the definition of 1 meter cubed is the volume of a prism of cross-sectional area 1 meter squared and height 1 meter. For speed or velocity, we know that speed or velocity is distance divided by time, or displacement divided by time. So the SI unit for speed or velocity is going to be the SI unit for distance or displacement, that is the meter, divided by the SI unit for time. So that is either meters per second, or if we like, meter second to the minus 1. For acceleration, acceleration is the change in velocity divided by time. We know that velocity is measured in meters per second, that time is measured in seconds, so acceleration is meters per second, or meters per second squared, or meter second to the minus 2. And finally, density we know is mass divided by volume. So the unit of mass is kilograms, the unit of volume is meters cubed. So density has got a unit, an SI unit of kilograms per meter cubed, or kilogram meter to the minus 3. Now, some derived units have been given names that honour the scientists associated with the establishing the importance of the quantities they investigated. And this is particularly the case in mechanics, where three famous British scientists gave their name to the unit of the quantities. So force is mass times acceleration. Mass we know is kilograms. Acceleration we know is meters per second squared, in other words meter second to the minus 2. So we could write the unit of force as being kilogram meter second to the minus 2. Or we can write it as newtons, because 1 newton is defined as the force required to accelerate a mass of 1 kilogram by 1 meter per second squared. And the newton is named after the famous British mathematician and physicist Isaac Newton. We'll be using newtons a lot within our work in both M2 and M4. The unit for work and energy, the formula for work and energy is force times distance. So we've got the force for the unit for force is kilogram meter per second squared, and we've got to multiply that by distance. So that's kilogram meter per second squared times by meters. So that's going to give me kilogram meters squared times by times second to the minus 2, or kilogram meter squared per second squared. Or we could say it was simply Newton times by meter, because the unit of force is the Newton. So the unit of work and energy could be written as Newton meters. Or we can say that a force of 1 Newton, which moves 1 meter in the direction of the force, does 1 joule of work. And that is named after James Joule, who was an English physicist in the 19th century. And the unit of power, which is work done by a force divided by time, can be set up as the unit of force, kilogram meter squared per second squared, divided by time. So that is now going to become kilograms meter squared per second per second. In other words, kilogram meter squared per second cubed, or kilograms meters squared seconds to the minus 3. Or we can say that it is joules per second, or joule second to the minus 1. Or we can define it as being the watt. 1 watt is the power developed by a force that does 1 joule of work in 1 second. The watt is named after James Watt, a famous British, or Scottish in fact, engineer who worked during the 18th century. Now we're going to use our knowledge of units to work out the units of a constant given by an equation. The force F of gravitational attraction between two objects of mass m1 and m2, which are distance r apart, is given by the expression F equals g times by m1 m2 divided by r squared. And we want to deduce the units of the gravitational constant, big G. In order to do this, we start off with the equation and rearrange the equation to make big G the subject of the formula. So we can first of all write F times r squared equals G times m1 m2, and deduce that F times r squared divided by m1 m2 must equal G. So we can say that the units of G must be the units of F times by the units of r squared divided by the units of m1 times by the units of m2. The units of force we know are newtons. The units of r are the meters, because r is a distance, so the units of r squared will be meters squared. And the units of m1, well, m1 is a mass, so that must be kilograms, and the units of m2 must also be kilograms. So we've got the units of G must be newtons times by meters squared divided by kilograms times by kilograms. So we can write that as being newtons meters squared kilograms to the minus 2. But if we want the units of G, we might well want them in terms of the base SI units. So we want to remove the derived unit of newtons and replace newtons by the fact that we know that newton is the same thing as kilogram meter per second squared, or kilogram meter seconds to the minus 2. So the units of G are kilograms, meters, second to the minus 2, times by meters squared, kilograms to the minus 2. In other words, we have meters cubed, kilograms to the minus 1, seconds to the minus 2, as being the units of G. As a second application, it's known that the speed v that a wave travels down a string depends on the mass, m, the length, l, and the tension, T, of the string, and that the equation linking these variables is of the form v equals k times m to the alpha, l to the beta, t to the gamma, where k is a constant number, in other words, with no units. We've got to determine the values of alpha, beta, and gamma. Well, on the left-hand side we've got v, which is a speed, so we know the units of v are meters second to the minus 2. We know that capital M is a mass, so that's kilograms for the units. L is a length, so the units are measured, L is measured in meters. And T is a tension, which is a force, so that is therefore measured in newtons, or kilograms, meters, seconds to the minus 2. So, the unit form of the equation v equals km to the alpha, l to the beta, t to the gamma is meters second to the minus 1, that's the units of v, equals the units of k. Well, we said k has no units, so we're not going to write anything there. We've got units, we've got m to the alpha, so the units of m are kilograms, so that is kilograms to the alpha. Units of l are meters, so we've got l to the power beta, so that's going to be meters to the power beta when we're thinking about the units. And then finally we've got t to the gamma. T is newtons, or kilogram meter seconds to the minus 2. But we want t to the gamma, so we've got kilogram meter second to the minus 2, all to the power gamma. Now if we simplify the right hand side, we've got kilograms to the alpha times by kilograms to the gamma, so that's going to give me kilograms to the alpha plus gamma. We've got meters to the beta times by meters to the gamma, so we've got meters to the beta plus gamma, and we've simply got seconds to the minus 2 to the power gamma, so that is seconds to the minus 2 gamma. Looking at each of the units on each side of this equation, then we're going to obtain 3 useful equations. On the left hand side, if we look at the meters to begin with, on the left hand side we've just got meters occurring to the power 1, so we can say that we've got 1 on the left hand side for the units of meters, but on the right hand side meters occur beta plus gamma times, so we've got meters to the 1 must be the same thing as meters to the beta plus gamma. In other words, 1 must be equal to beta plus gamma. If we now look at the units of seconds, on the left hand side we've got seconds to the minus 1. On the right hand side we've got seconds to the minus 2 gamma. So we must have minus 1 equals minus 2 gamma. And then finally, if we look at kilograms on each side, on the left hand side kilograms don't appear at all, so we've got kilograms to the power 0 on the left hand side must equal kilograms to the alpha plus gamma, so in other words we've got 0 must equal alpha plus gamma. Solving this system of equations, well, we get gamma equals a half, in which case alpha must be equal to minus a half and beta must be equal to plus a half, and that now tells me that the equation for v must be of the form v equals k times m to the minus a half, L to the half, and T to the power half. So we've been able to use our knowledge of units to get the format for a rule, a scientific rule.